It's on now, so you don't have to worry about that, and you can stick that in your pocket. I'm gonna walk over here, and that camera's gonna you in a second.
Not yet. You can still talk.
Nobody will feel cheated if they miss your part.
Exactly what I was thinking. So we'll start 1 minute early so that if somebody comes in. So I want to welcome you to, we don't know exactly, but something like the 17th or 18th Simons Lecture. So this is the math department's distinct most prestigious lecture series, obviously funded by the Simons Foundation. And it's been going on since about 2000. And there's, as has been the tradition, not quite from the beginning, but close to the beginning, there's actually two. There's an applied version and a pure version. This happens to be the applied version. I'm not sure you'll be able to tell the difference. Our speaker in the applied version is Yuval Peres, who's principal researcher at Microsoft Research in Redmond, Washington, and adjunct professor at UC Berkeley in statistics and mathematics. His PhD is from Hebrew University in 1990 under Hillel Furstenberg, and was at Hebrew University and UC Berkeley before joining Microsoft in 2006. Yuval is known for contributions to all parts of probability theory, also theoretical computer science, ergodic theory. He's worked on random walks, random motion, percolation, Markov chains, et cetera, et cetera. He's the author of 250 research papers, 5 books, serves on many editorial committees, supervised 21 PhDs, and he's winner of the 1995 Roller Davidson Prize, the this is the French bit, the Webb Prize in probability in 2001, and the 2011 David R. Robbins Prize at the MAA, and he's given many distinguished lectures series before, including at the International Congress in 2002, and he's a fellow of the American Math Society and a foreign associate of the National Academy of Sciences. Without further ado, Yuval.
Thank you, Thomas. It's a real pleasure and honor to be here. And so I hope you'll find these topics interesting. The first topic will be joint work with Nina Holden, who is a student here, and Alex Jai, a student at Stanford. And before starting on the topic proper, I want to mention it's related to one of my longest interests in matching, kind of two-color matching. Let me show you some older slides that pertain to that. So here is an example of a two-color stable matching. Maybe I'll show something about that. So we're going to working in the main part of the talk on the sphere, but this is something that makes sense in the whole space as well. So we're going to have blue and red points, and we're going to be interested in matchings of the blue and the red that are optimal in various senses. We'll see later there's kind of an MIT connection to that as well. So one natural sense is the greedy matching, which is also the stable matching. So in the greedy matching, you have the blue and red points. If a blue and red points are mutually closest, right? So this blue point looks at all red points, and it's find one that's closest. And the red point looks at all blue points, and it's find one that's closest. If there are two that are mutually closest, we match them, take them out of the game, and repeat. So this can be thought of as a kind of greedy matching, but it's also stable in the sense of Gale-Shapley. So there are no unstable pairs. So when you finish this greedy matching, if you have a blue and red point that are not matched to each other, we would say that they're unstable if they prefer each other, they're closer to each other than their matches. So that's stability in the sense of Gale and Shapley. And there's a unique stable matching, not in the general setting, but in this setting of where it's determined by distances. There's a unique one, and here you see what it is for this ensemble of points. On the other hand, another natural object would be to look for the matching of minimal total length or average length, and this is what you see here. So in terms of total length, this is much more efficient than the other one, but on the other hand, this one is unstable. So if you look closely, you'll find a blue and red point that are not matched, but are closer to each other than their matches in this one. So this an example of a contrast. One open problem I'll mention at the end, but might as well mention it here. So the minimum length matching has been understood basically since 1984, worth of work of Aitai, Komlos, and Tusnadi, who showed that if you do this if you throw n blue points, n red points in a square of area n, then the average length of this optimal matching is order root log n. So I'll state this more formally, but we showed it's order root log n. Now, of course, we have very nice algorithms to find minimum matching, but nothing can be simpler than this greedy algorithm, which is not optimal, you can see from the picture. However, as far as I know, there is no analysis yet of how well or how badly does this do. What's the average length in this case? So it looks like such a simple algorithm. So we know bounds that are very far apart. I conjecture it's log n, but we really don't know. So I'll come back to this point. But I want to mention that we don't know the analysis of the greedy one, and we'll see another one, the gravitational method, which looks much more sophisticated, yet we can analyze it. So with that, I want to start with the topic of today. And I'll say more about kind of background and previous work as we go along. So again, before we get to matchings, our goal will be a fair allocation, and maybe let me go back and show you another fair allocation more related to, again, from previous work. So this is another example of a fair allocation. So we have these points thrown at random in a square. So now there's just one class of points, these centers or stars that are thrown at random. Here they're on the square. Later they'll be on the sphere. So what you see here, this is a picture drawn by Ander Holroyd, who was a co-author on that work more than a decade ago. So what you see here is the stable allocation. So the goal is each center is allocated a territory of the same area. So we want to divide the total area equally among these centers. So here it's on a torus, so the left and right boundaries are identified similarly for top and bottom. And how do these points obtain their territories? Think of each point as growing a disk around it at unit rate, capturing all the area it reaches first, and continuing until it gets its allotted area. So say we have 300 points here and the total area is exactly 300, then every point will continue until it's gotten a unit area, and then it will stop. Now some points are lucky and they get their area kind of locally, so they basically get the disk. But some points are hemmed in by other points, and then when they, so you'll see many examples in this picture. So like if you look at this one here, right, you see this one, it's kind of hemmed in. So as it grows the disk, it only gets a small sliver area nearby. So it keeps growing this disk in the background. Eventually it resurfaces here when other points that were in the way got sated, and it gets its remaining area here. So every point will eventually get the right area, but its territory may be disconnected. Anyway, we analyze this. This has some nice properties. It can be done with the Poisson process in the whole plane or the whole space, but the territory can be rather unwieldy, disconnected, and also the territory of a point could go very far. So if you think of it as a random variable, how far is the distance from a point from a center to a typical point in its territory? This random variable has large tails. And so even if you do this in higher dimensions, it will have some power law tails, and in 2 dimensions, again, it will have some power law tails, but we'd like to get something where the sets are less dispersed. So that was so that was one method, and it's kind of built in to create equal area because of the stopping rule, right? The territory grows until it attains its right area, and then it just stops. So now I want to tell you, so in general, we'll still be interested in fair allocations. That is, to each center we want to allocate exactly the same area. We'll see the connection of those to matchings as we go along. And we'll want to find kind of better allocations, say where the territories are connected and don't extend as far. Okay, so we want to divide torus, or in this case, today we'll talk about a sphere. So we're going to take a sphere of area n. Everything can be done on a torus, but what I'm talking today fits best on the sphere. So we'll take a sphere. So SN2 means a 2-dimensional sphere sitting in R3 of area exactly n. So its radius is a constant root n. Okay, so this will be the object we'll be working on mostly. And we want to partition the sphere into cells. So here is that sphere. Here are these stars or centers. And we want to partition the sphere into these equal territories, one for each center. The pictures of gravitational allocation I'll show you were created by many people, including my co-authors Nina and Alex, but they're based on code originally written by Manjunath Krishnapur. Okay, so again, formally, an allocation rule will be a mapping that takes a collection of points to the allocation, to the fair allocation psi L. So remind you, psi will be the map that takes a point on the sphere to the center it's allocated to. And we want to minimize the typical behavior of psi of x minus x. Now, one thing I won't emphasize, but is really we want of an allocation rule that will be equivariant under rotation. So if you take the collection of points and rotate it, we'd like the whole picture to rotate with that. We don't want a rule that is kind of coordinate dependent. All the natural rules one talks about have this property. Okay, so we'll see how a fair allocation and eventually a matching arise from using gravitation. So we're going to start with the standard two-dimensional potential, but these are points in 3 dimensions. So these are points on the two-dimensional sphere in 3 dimensions. So we take the sum. So u of x is the sum of the log of x minus z, where we sum over z in the collection of stars in this L. L is the set of centers. And we're going to, so this will be our gravitational potential, and then we're going to have a gravitational force field, which will be minus the gradient of the potential. But because the points are, because the points are on a sphere, right? So say if you look at a point here, the force of gravity, if you just take the gradient of the potential as I defined it, it would point into the, into the ball. But the points are restricted to stay and move just on the sphere. So we're going to take the gradient and take its component on the tangent plane of the sphere. Another way to think of it is you take a gradient with respect to the spherical metric. Okay, so the force is you just, so the force acting on, so every point in the sphere has this force, has a potential determined by the stars, and then it will move with the, according to this gradient field, but restricted to stay on the sphere. Okay, so here is again a picture illustrating what we're doing. So we're going to look at the point x. So here's some typical point x. This will be the point z that x will eventually flow into. And so we'll be using the gradient flow. So yx is the path that the point little x will follow. And so note that this is sometimes called Aristotelian dynamics, because Aristotle reportedly thought that forces impact the velocity of particles. So we're going to follow Aristotle rather than Newton. So the forces won't give us acceleration, they will give us velocity. And this is actually useful for having the particles go into the stars rather than, say, fly by them due to inertia. So we really want the particles to go directly into the stars, and the Aristotle method does that for us. So again, we're going to use this force field as a gradient to define a gradient flow, very simple differential equation on the path starting from any point x. Okay, so this is the path that x follows, and almost every x we will see. So there are some boundary curves, but almost every x on the sphere will flow into one of the original stars, according to this. So here is a particular star Z right here, and it has a basin, this kind of green basin, and x, every point x in the basin just flows according to this gradient flow into Z. Okay, any questions? Yes?
What's the absolute value of x minus z?
So this is just the L2 norm. Distance, just distance, no. Distance in R3. Thanks for asking. So tau sub x is the time that x gets swallowed in z. So we have a flow, it's a function of time, and it turns out almost every x at a finite time it gets swallowed by some z. So that finite time is tau sub x.
Wait, just to be clear, this gravitational process is basically the same thing as a continuous version of gradient descent running on that potential.
Yes, right. So, so psi of x is the terminal point that from every x, if the flow leads to star z, then we define psi of x equals z. If x is not in any basin of attraction, we'll just define psi of x to be infinity, some bad point outside the sphere, and this will happen with measure 0, as we'll see. Now, I claim that this defines a fair allocation. And this is somewhat surprising. So look at this situation. So, the points are thrown at random. So look at this star, which is kind of hemmed in by the other stars, or this center hemmed in. It doesn't look likely that it's clear that it will get some small neighborhood here, but how could it get the same share as the other points? I'll tell you, I'm giving a talk on this topic also in the Math Congress of the Americas in Montreal, and I submitted my abstract, and the professor who was receiving the abstract happened to be a math physicist, and when I sent him the abstract, he sent it back and said, you must have some error here because this is impossible. You must have some weights and so on. So, and he sent me, this scenario, and he said, obviously your method has to fail here. So, luckily we could, we could send him this picture. So, the colors on this picture are not perfect, so I apologize. So here, the domain of attraction of the center point is what you see in kind of pink and white here. And then you have these other domains. So the basin, anyway, so the key thing is the center point gets area, not just from nearby, but there are also points here that even though they're closer to these stars, they don't get swallowed by them because of the gravity force balances, and they just travel all the way to this. And miraculously, when things, when the dust settles, this center gets exactly the same area as the other in this scenario. But then, another kind of worrying setup is this. So suppose you have like 1 point in the South Pole and 7 points, you just see 4 of them in the North Pole. So it looks like this one, should get a lot of area, right? But it really doesn't. So again, this is its domain. So the point is that these points are teaming together and kind of pulling things that are here that are much closer to the South Pole. They still get pulled all the way to something in the North Pole because of all the force coming from the points on the Northern Hemisphere. Yes?
Is this particular just to the sphere?
No, it's particular to using gradients of harmonic potentials. So, okay, well, these are not accidents, and let me indicate a proof in this setting. So this proof doesn't have all the details. In particular, I'm going to assume here that the boundaries are piecewise smooth, and the real proof kind of avoids such an assumption. But again, so let's assume that a basin, let's look at the basin of a point Z, and assume it's piecewise smooth boundary, and that we can apply the divergence theorem in that boundary. Actually, we have to move a little bit inside the domain to make this, rigorous. But anyway, so remember, F, the force, was minus the spherical gradient of the potential. So the divergence theorem tells us that if we take the divergence of the force, which is well, minus the spherical Laplacian of u, then we'll have this identity. The integral, so I put the minus sign, so the integral of the spherical Laplacian of u should equal minus the integral of the force on, and this is a line integral on the boundary. Now, this potential logarithm, it's a exactly harmonic function in logarithm of absolute value. It's exactly harmonic in 2 dimensions. But because of the curvature in the sphere, you'll find that its Laplacian will be minus 2 pi at all points except the singularities. And at the singularities, the Laplacian of the logarithm will give you a delta function. So this you have to understand in a distributional sense. Anyway, this is a very standard calculation, Laplacian of a logarithm, and it shows that you'll get exactly 2 pi times the sum over all the points, all the stars, a delta in each star, minus 2 pi. But the other important point is that the force if you look at these boundaries, then the force on the boundaries is parallel to the boundary, because if the force was pointing in one side or the other, then this wouldn't be a boundary. This would be a point inside the basin. So on the boundaries, the particles can't decide, do I want to go to Z1 or to Z2? So the force is actually parallel to the boundary in these, so you saw there was a picture. So if you look at any kind of boundary here, then here so inside here the force is going this way, but on the boundary the force vector is parallel to the boundary, and hence when you multiply it by the normal, so n is the normal vector of the boundary, this is just 0, and so this right-hand side integral is 0. So this left-hand side is 0 on a basin. But if we look at one basin, we just have a single delta function there. So the sum boils down to just just 2 pi. And when we integrate this part, we'll get 2 pi times the area. So lambda here is just the area measure, times the area of the basin. So the area of the basin is indeed 1 for each one. But this proof reminds me of a statement by Knuth when he sent some software to a colleague, and he said, beware of this program. I've proved it correct, but I haven't yet tried it. So when you see this proof, you think, okay, I'd like to really see if this works. So this works, and there's also a more detailed, completely rigorous proof with all the detailed filled in, but this is, the idea why this is true. Again, any questions? Yes?
Wait, so you're applying the divergence theorem on this space that's curved space or whatever. So,
Yeah.
so that is kosher, or I don't even know what the theorem is.
Yes, Stokes' theorem. But you can also, if you like better the divergence theorem on the plane, you can apply stereographic projection from the sphere to the plane, and there. What? And so it's all. So the Laplacian just moves to the Laplacian. Actually, this logarithm of absolute value changes. There's a correction term when you do the stereographic projection. So in the paper, which will be on the archive tomorrow, you can see these kind of calculus details worked out. Right, so you have to rotate in the correct direction.
So, looking
Yes.
at this, it seems like the areas of these basins are what, regardless of how many charges you have on the sphere?
No, so it's so yeah, so it is. So it does use the fact. So there's something So as I said, there are some things I'm omitting here, but one thing is that when you take the Laplacian of u, one thing you know abstractly is that if you take, since you have a closed surface, if you integrate this over the whole surface, you must get 0. So anyway, we'll see another explanation shortly. Okay. So that's right, and in fact, the higher dimensions were understood before. I'll tell you. So there's in 2 dimensions you can only do this in finite volume. In higher dimensions you can do this also in the infinite volume. Yeah. So also, okay, it's because if you want the Green's function, or because the gravitational force doesn't converge. So okay, so this is how it looks with 15 points, with 40 points, 200 points, 750 points. It really works. So a bit about, so this project didn't come out of nowhere. So the first time that such a gradient flow was analyzed was by Nazarov, Sodin, and Volberg, a paper in GAFA 2007. In fact, Sodin had told me about this idea in a few years before, and he said, we think this could work, but we're too busy, so why don't you work it out? So I was excited. I tried to work it out. I actually couldn't, but I had a student, Manju, who drew a picture of these domains. I sent the picture to Sodin, and he said, okay, we're dropping everything. We're going to analyze what's going on here. And they did, but in their setting, the points were not random points. They were the zeros of a shift invariant Gaussian analytic function. So maybe I'll write down the formula for this function. So you take a sum of ak over root k factorial z to the k, where the ak are standard complex normals. Okay, so real and imaginary part are complex. Real and imaginary part are standard Gaussian. So you look at this series, it converges in the whole plane, and you look at its zeros, and by looking at the covariance function of this series, you can recognize an exponential, and it's classical that the zeros of this series are a translation invariant point process in the plane. In fact, it's the only way to get translation invariant process from zeros of a Gaussian analytic function is this up to scaling. So it's a very canonical series, and they were looking at these points, and then they weren't thinking of gravity at the time, but they were applying this potential. So you take log of the absolute value of f, and there's some reason to make this correction. And but the basic thing behind this is log of the absolute value of a analytic function gives you a harmonic function. So they're applying this potential and similar gradient flow and getting equal areas. And here they can do this directly in the whole plane. So this set of zeros here is much more rigid than random points, much fewer fluctuations. And so one can, and what most important, the potential is given by an explicit formula that you can analyze, because this series you can understand exactly. So they were able to beautifully analyze it. And after they did that, then with Shurav Chatterjee, Ron Peled, and Dan Romick, we built on their work to analyze the case of random points. So this would be uniform points, or in the infinite space Poisson points, in the whole space, so in RD. But we could only do this for D at least 3. So again, you have the standard gravity force acting on every point, and then standard gravity force implied by the stars. The stars are now a Poisson point process in all space, and a point, again, you have a point flows with this gradient flow according to, and goes into one of the stars up to measure 0. So all these considerations apply there in both of these settings, and the kind of rigorous version of the proof I showed you works in these settings, but it doesn't work in 2 dimensions. So the problem in 2 dimensions, if you try to add the force, if you say are working in the whole plane, then the series defining the force diverges. So in 2 dimensions, as you add more and more points, you get new terms that just, so the force acting on a point, it spins around and around, doesn't converge. So we can't define the gravitational allocation in R2, although the stable allocation I showed you at the beginning works fine in R2. So I always had in mind to go back to the 2-dimensional case and understand it with a finite collection of points. And here it's natural to do that either on the torus or the sphere to get some invariance. And that's what we're doing in this project. Now, the result again suggests why there would be trouble doing this in the whole plane. Concerns, I stated, so this is the theorem about the behavior of the allocation on the sphere. So the distance in the gravitational allocation between x and the star it goes to is, on average, bounded by root log n. So constant root log n. So if you take a sphere and drive the radius to infinity, so the sphere gets flatter and kind of converges to the plane, but the right-hand side will diverge, and we'll see there's a reason for that, and this is really the right order. Okay, so I want to connect to the matchings that I started with today. So a corollary of the allocation is that we can get a matching, a gravitational matching between blue points, B1 to Bn, and red points, A1 to An. So I want a bijection phi from A to B, so that the average distance, so here x will be the average distance between a point and its image, this average will again be bounded by constant root log n.
These points are being chosen uniformly?
Yes. So this is going to be 2 endpoints, n red ones and n blue ones, on a sphere of area n thrown uniformly. And we are looking to match them and asking for the distance in this matching, the average distance. So in fact, there's a theorem of Aitai, Komlos, Tusnadi I referred to from '84, and they were working in the square instead of in a sphere, but these things are equivalent. And so they were looking for 2 endpoints in a square of area n, and again they showed that the average mapping distance is of order root log n. And this is for the optimal matching. So we see here that the gravitational method, which I'm about to tell you, achieves up to constant the optimum. Okay, so how do we get the gravitational matching? This is kind of a general black box type of deduction. So we start with n blue points, which we call B here, and they define the gravitational potential and in a partition of the sphere, but we're not going to use the partition explicitly, it will be implicitly behind. Now, the red points, we're going to throw in one by one. So A1 is the first red point, and with probability 1, A1 will flow into one of the blue points. So that's how we define phi of A1. Now, the key thing is phi of A1 is a uniform choice among the n blue points. That's because of the equal area theorem, right? So, because all these regions have equal area, a red point falling at random has equal chance to fall in each of these basins. So it means that the blue point that we're going to remove, that will be matched, is uniform among the n blue points. So we started with n points uniform on the sphere. Now we choose one uniformly at random and just pluck it out by this matching. The n minus 1 that remain are still n minus 1 independent uniform points on the sphere, because the one removed is uniform. So now we can just repeat, right? Throw in another red point, see where it's matched, and so on. And if we look, what's the behavior of this matching? So we understand it at every stage. So if we look at when the first point fell, its distance, right? So let me go back to this one, right? A1, it's a random point. So its distance to phi of A1 is covered by the previous theorem. So, so its distance has expectation, which is at most root log n. And so this is true for each of these. Now we do have to remember some scaling, because when we have the n points, we define it on a sphere of area n. When we're down to k points, the root log k is true if the sphere had area k. So we have to scale by root n over k to take that into account. That's why we get this root n over k. Now we stuck in a 1 here just so that we wouldn't be frazzled in the case k equals 1. So, yeah, so instead of root log k here, I put root 1 plus log k, so it's still fine when k equals 1. And then we just are going to get a bound which is up to constant, the average of this sum, root n over k, root 1 plus log k. And if you just bound this by root log n and perform the sum, you'll see a bound of constant root log n on the total. So we're getting an optimal matching and expectation from this gravitational procedure. And note that to do this, you don't have to compute this complicated map. This was used in the proof, but to actually implement it, you just throw down a red point, and now you just need to understand the forces on this particular red point, which, you know, with multiple methods, you can calculate gravity extremely efficiently. So it's actually a pretty fast method to get an almost optimal matching. And nice thing is this matching algorithm is online, or more precisely half online, meaning that the blue points have to be there, but the red points can arrive one by one. I don't need to know them all in advance. When I decide on phi of ak, I just need to know the previous k points, and I don't have to know the future points. Now, one thing that online matching can't achieve is the Shor and Leighton-Shor theorems that talk about another parameter, say a finer parameter. So instead of worrying about the average length of the matching, one can worry about the longest edge of the matching. And that's a finer quantity. This is a famous work of Shor and Leighton-Shor from the 80s. And it says that if you are interested in the longest edge, then the best matching will behave like log n to the 3/4. So I'm just to remind people here of this result. We can't do anything gravitational to reproduce this or to understand this, and to emphasize that any online method is going to fail this, because when the last point or red point arrives, there's only one blue point left, and that distance can be huge. It's going to be, so the last term is going to be root n when you do online. So so for the average, the last few points don't really hurt us, but if you're worried about the longest edge, then you can't do online. I was just chatting to Peter before the talk, and he reminded me that it's still an open question whether one can have one matching procedure that will be good both for the average and for the maximum. Optimal, almost optimal for both. So the procedures that are known are different. Okay, so in higher, so 2 dimensions is where the action is. So what happens in higher dimensions is that everything is, so if you normalize correctly, so you throw down n blue points, n red points in volume n, then the average distance is a constant. So it doesn't scale with n, which also tells you that why, or suggests that you should be able to do this in infinite volume. Okay, so I mentioned in the beginning the challenge of understanding the greedy matching. So you iteratively match mutually closest points, or you could just take the closest red and blue point, match them, and repeat. So I don't think many people have worked on this. There's a paper I wrote with Holroyd, Pimentel, and Schramm, where we considered a different problem, but as a consequence of that, one gets a bound which is about n to the quarter, a little worse, and I believe it's far off for the greedy matching. So you have n blue points, n red points on the domain of area n, or on the sphere of area n. Look at the greedy matching. We're far from understanding that, while the gravitational we understand pretty well. So let's see, when we have till? Okay, good. So let's. So I want to tell you some of the ideas of the proofs. So note that. Okay, so psi of x is going to be the curve starting at x at the terminal time tau x. So we can write it as this integral of the force. So to bound the size of this, above, it's enough to bound the time we travel and the magnitude of the force along the curve. Okay, so this slide is a little too dense, but I'm going to give you some more details in this. So it turns out there's a beautiful formula coming from a classical Liouville theorem that says that this time tau x to be swallowed by the star has an exponential distribution. In particular, it's typically small. So it's certainly bounded in expectation. So I'll explain that a bit. So points are swallowed quickly. And the other thing is, if you have a point and you want to see what's the force exerted on it, well, if it has a star nearby, we know that that force is going to be like 1 over the distance. But if there's no star nearby, and nearby turns out to be 1 over root log n is the right distance to look. If there's no point that close, then the force, overall force on the point is determined by the faraway points. And to determine that, these points are random. And when you look at points at, so this is a rough argument, again. So if you look at the points in an annulus, a distance k, so points at distance, right? So I have some, okay, so actually let's take here z equals y. So I have a point y, and I want to see what's the force on it from this annulus. So this force is random, but to understand it, just think of dividing this annulus into little regions of area 1. So there are k such regions. And in each one, we expect about 1 star. And so the force is going to be a sum of all these terms. Each term is going to be random and of magnitude so each term is going to be random of magnitude 1 over k. So if I look at the variance of the force, I'll be adding terms of order 1 over k squared, and I'll be adding k of them. So the overall contribution of this annulus, if I look at the target point, at a particular point, I look at the overall contribution of the variance of the force as applied to this point, it's going to be 1 over k. And then I have to sum this over the different k, and you'll get that the variance of the force, so the force on a point is random, and it's unbiased, and its variance is logarithmic. So the magnitude of the force is typically root log k. So this means a point will travel to the faraway galaxy that's pulling it with a with a force of root log k. When can a local star deflect it from this path? If it's closer than 1 over root log k, because that means that the local force will dominate this global force. So a point will travel until it gets at random close enough to such a star, and then it will just veer into that star and fall into it. That's a very rough description of what happens, and that's behind the bounds for. So this force, most of the time, is going to be dominated by root log n until, because that's going to be the global force, until a nearby star is detected, and then we fall into that star very quickly. So the force explodes, but it's a very short time, and this last piece is integrable. So overall, what dominates is the root log n that happens over time. Now, the kind of a key fact that's behind much of what we're doing is this, the exponential tail of the swallowing time. And this is based on the beautiful classical Liouville theorem. I don't know who remembers it. It reminds me when I was a postdoc, I asked Peter Jones, my mentor at the time, a question. He said, "This is so classical, nobody remembers how to do it." So I admit I didn't know of Liouville's theorem until working on this topic back in 10 years ago. So, but what does it say? So here's one version. This is not exactly the words Liouville used, but we have a two-dimensional manifold, a smooth vector field, and the flow induced by it. And we're looking at the image. So this flow is going to take the domain to a new domain, and for us, the flow will kind of contract a domain. Yeah. So, right. So the derivative of the volume of this domain is given by the integral. So at time 0 is the integral of the divergence of the force. So so Arnold's book on classical mechanics is one place you can read about this. So how is it useful for us? So look at the points in the basin that are swallowed after time t. Okay, and Vt is the volume of these points. Okay, then what is the volume of Vt? So let's start at time. So let's look at omega is Vt minus s. And look at this derivative. So Liouville's theorem basically tells you that the derivative is going to be, in this case, 2 pi times the volume of the region. So this is because the divergence of the force is just the Laplacian of the potential, which is a constant except at the stars. So since we're looking, in the region in the basin, we're just going to get this constant. So we can solve this differential equation. It gives us an exponential, and that's what is behind the fact that so the volume Vt is just e to the minus 2 pi t times V0. Okay, and so if you look at so this is V0 are all the points that ever, it's just all the points in the basin. So okay. All right, so the final so there are several directions this goes. One is one is understanding greedy matchings, another is understanding gravitational location in other settings, and there's interesting work in progress by Ding and Peled on the case of a hyperbolic plane, and this is just some of the pictures that correspond to their analysis. I'm going to so end with that. Thank you.
Are there any questions?
So it seems like your algorithm for matching works also if an adversary doesn't let you choose like all the red points, say.
Uh-huh.
You can still obtain like a good average length matching.
Well, no, you can obtain a matching. The average length could be much worse. So the analysis of so it's true that you'll still get, say, if the blue points that I started with are not uniform but just arbitrary generic configuration, then when the red point falls, it will go to a uniform blue point. That part of the analysis is true. But when you want to see how far it will travel, that depends on the shape of these domains. And if the blue points are not random but are arbitrary, then these domains could be much longer. And so the travel distance could be very, very large. And you can easily see if all the n points are clustered near the North Pole, and then you're throwing the red points uniformly, the matching distance is going to be the average distance is going to be average the diameter of this sphere. Yes.
So in a way, you're transporting the uniform measure on the sphere to the empirical measure of your.
Exactly.
Is there a way to in which this gravitational allocation is computing some optimal transport with respect to some norm?
So it's not. It doesn't seem to be it's not optimal with respect to any norm we know, but it's approximately optimal with respect to Euclidean. Yes. Pavel?
This is a kind of similar to Sam's question. So, what if you're allowed to plant, let's say, blue points, trying to make this average as small as possible? Can you do better than square root of log n?
Sure. I mean, if the points come from a more rigid processor, which so there's zeros, there's Gaussian polynomials that are naturally defined in the plane but then the zeros, but when you map stereographically to the sphere, they are rotation invariant. So there's a great survey of Sodin, and also I have a book on these kind of things. And so those are much more rigid, and there the average distance is 1, not was order 1. So this is really, the root log n is really capturing the fluctuations of random points.
Natural questions after that is whether the prefactor C is well defined as n goes to infinity. What about the variance, concentration, things like that?
Well, that's why I came to give this talk here. So the right people will.
Doesn't follow. For example,
So
concentration.
So in higher dimensions, we understand what happens because things converge on the sphere, they converge to the whole space. So you have a limit. But so there's no root log n, there's no normalization. So you just get, so in dimension 3 and higher, all is well. In dimension 2, you have to normalize by these root log n factors. And of course, we would conjecture that there will be a limiting constant, but that's still to be shown.
What about concentration? What's the total air allocation around n?
Of
Concentration
of the
cost function that you get by this allocation.
again, for a fixed domain, of course, it won't. You're talking about for the allocation, right? We're looking at a fixed domain. There won't be any concentration. But you mean for the average?
As n goes, you have n blue points and red points.
No. Okay, so you're looking at the matching, not the allocate. Yeah, for the matching. For the matching, I'm sure there's concentration, and maybe I think the formulas we have are enough to to show that. Yes.
My earlier question, you had a slide where you referred to a paper in GAFA, and there was an expression of log z minus z squared over 2.
Yes.
If I take the Laplacian of that, the log z gives me delta functions. The z squared over 2 gives me 1.
Right.
And so if I scale that second term with a constant, that fixes the size of the domain. Otherwise, the net charge in the domain would be 0, and I get a contradiction.
Right.
So now I still need. So it's just fixing constants like this that it all works out.
Right. So the constants here are fixed by the curvature. So because I took a sphere of area n, so
I'll work it out. Yeah.
yeah.
Okay, I think we've worked Yuval enough for one day. So let's thank him again for one.
So just one comment, the talks are independent of each other. They have some common thread of using potential theory, but if you didn't like this one, you might like the next, and vice versa.
So you mentioned at the end there's a hyperbolic version of the Gaussian entire function.
That's right. So
Your microphone.